I think it's a complete, yeah, it's definitely a complete projectile. That's a good question. Jacob Kenzie asked if, it's gonna be, I'm talking to Jacob. Hey, Jacob! You're probably on a lot of drugs right now. Yeah, his mom emailed me and said, you know, he's going under anesthesia, and then he's gonna try to come in. I'm like,
you sound just like his mom, too.
She's very sweet, isn't she? Yeah. She's very, very nice. All right, so the projectile motion problem, I will tell you this much. It's going to be a projectile shot at an angle. So let's say V, theta. And what kinds of questions could I ask about that? Sure, what's the angle? What else?
How far did it go?
How far did it go? The horizontal distance, right? Distance horizontal. Tallest point, good job. Yep, what's this? Time in the air. We've done a lot of these, so you should definitely go back and review, take a look either in your notes or if you took notes on previous tests, or go to the workbook. Some kids find the textbook very, very helpful. Other kids never open it. I know one thing that would be really helpful if you get off your phone. I'm keeping this till the end of the day. Go ahead.
Do you know what chapter in the workbook this is from?
No, not off the top of my head. I think it's chapter 4, but I don't want to be, yeah, you'll find it when you look it up. It's for like chapters 2 through 8, pretty much, yeah. Yeah, you'll know when you look at it. Okay, other questions about this list? Manraj?
I have 2 questions.
Yes.
So like the flying pig stuff, do we
Yeah.
have to know anything about that? Like, either like the concept of the flying pig or the math of it?
Conceptually, it'd be good to know what's going on with the flying pig. You won't have to know mathematically necessarily. Sure. The flying pig makes, when she's flying, she makes like a cone shape, right? And there's 3 forces. What are the 3 forces? Gravity, which I'm going to draw it here because it'll make the triangle more obvious, right? It's actually right here, but we're going to move it over. What else? Tension, yeah, which tries to do this, right? Counteracts gravity. And what's the other one? Centripetal, which is the horizontal. Okay? So, and the faster the pig spins, what happens? The faster her speed, how does that change this triangle? Right, so centripetal force increases, so this vector gets longer, and what'll that effectively do, make her do?
More force.
Yeah, bigger circle, that's correct. Because the string is limited in terms of its length, she'll like appear to kind of raise up a bit, right? So she gets more elevation. If she's heavier, then what happens?
Gravity pulls her.
Yep, that vector becomes longer and that, yeah, pulls her in more. Okay. So you had 2 questions on that?
Yeah.
Go ahead.
For the pulling problem, is it going to be like complicated like those last 2 problems that we have in the worksheet, or is it going to be more like the 3 before that?
Somewhere in between those. If you know how to do the complicated ones, you'll be fine. Yeah. The one on the marking period exam, I could show you that one, is similar. I think it's maybe a tad more complicated than this. We pick one that you got right. There we go. So similar level of difficulty. Notice there were a couple of hanging weights, but I didn't have multiple strings. It's more of a time issue than like you know, concepts. So yeah, if you could do this, you would be definitely well prepared for the semester question on pulleys. Other questions?
Number 4, which is equilibrium.
Yeah. Equilibrium are these questions. So like ups equals downs and lefts equals rights. So you would find, let's say this is M, then the vertical force, if it's in gravity, is mg. Let's call this T1. Let's call this T2. Call this theta 1, theta 2. Obviously, I'm going to give you some of the numbers. It's not all going to be variables. So you're going to find all the components. T1 cosine theta 1, T2 cosine theta 2, and then the vertical components, T1 sine theta 1, T2 sine theta 2. Okay? So what would the horizontal equation be? We're just using variables, but obviously you'll have numbers. Yep. And vertical? Very good. You could do minus mg equals 0 or equals m to either one of those is fine. Yep. So ups equals downs, lefts equals rights. F equals ma. Incline or friction? Incline? Sure.
Don't they both have friction?
They can, so I'll throw friction in. That's mu m. Say it's accelerating down the hill, some angle theta. You'll have to use the good triangle here. So this will be mg. This is also theta. The normal force is mg cosine theta. The parallel sliding force is mg sine theta. So what's the acceleration given all those variables? So F equals ma. The forces are gravity trying to slide it down the hill, and friction, of course, being negative, which is mu times the normal. And this is the normal force. So since it's sliding down the hill, we'll have mg sine theta minus mu mg cosine theta equals mass times acceleration. And in this particular problem, I wouldn't even have to give you mass because it's in each algebraic expression.
Would the one with friction just be like more simple? What would be the solid for that?
Yeah, it's the one with friction could have other forces since it's not going to be on an incline. It's a little more complicated. So let's say that we're pushing this like that at some force F, right? And it has a mass m. And let's say we accelerate it to the right. So if that's theta. So you'll have a parallel force like this, F cosine theta, and a perpendicular force here, F sine theta. And you'll also have gravity. Okay? So what force will slide it?
Cosine theta.
Yep, F cosine theta. Oh, I gotta put some friction there too, so friction is there. And what force will slow it down? Right. So again, if F equals ma, then F cosine theta is the force that makes it go, minus mu times the normal, that'll slow it down. And the normal force is a combination of both of these. Now, in this particular equation, you can't cancel the math because it is not in every single algebraic expression. All right, 10 minutes, we'll pause it. You guys can take a lap, and then we'll come back.